Okay, so now we're recording. Okay, that's a picture of me. I hope you guys are having a good week. We are in chapter 10. We started something new, so we only have one section, really, section and a half under our belt. And remember that we started chapter 10 and it's all about circles. So circles. We on Monday talked a lot about the definition of different parts, not parts of a circle, but different lines, points that can go through a circle. So a circle, remember, has a center. Our most important thing is the radius here. So the radius is basically from the center to any point on the circle, it's equidistance. And then we've talked a lot about this tangent here. So the tangent actually hits the circle at one point and it actually hits it at 90 degrees. So that's a couple things to remember from that. Okay, so that is a circle. We also started in 8.2 a little bit. So I think 8.1 everyone felt really good with. We started talking about the arcs of a circle and what that looks like and how to measure the arcs of a circle. And I think everybody did a really great job of understanding what that meant. This is a poor squished circle here, but let's do problem number 1 just to kind of review some of our terminology here. So let me open it up here and try to unsquish our, well, this is supposed to be a circle. Okay, so we know that we have a circle. All circles add up to how many degrees? If you measure the degrees around a circle, what does that add up to? Anybody? Oh, you can't see the screen. That would be a problem. Let me share my screen with you. Probably like, what is she talking about? Okay, is that better? Awesome. Okay, so we are in section 10.2 called use properties of tangents, but we're talking about starting talking about arcs and what that means. So if I have this circle, I made it a little bit bigger here, and I am going to attempt to draw the diameter here. So that's supposed to go through the center. Okay, so that's a diameter, right? And then I also have a radius that goes through the center. It's kind of like my picture here. Okay, so I'm kind of recreating this drawing here just to review a few things. P right here is the center of my circle, right? That's the center. Everything is equal distance from that. I have on my circle, I have labeled, this is R and this is S, and this is 45 degrees. 45 degrees. Okay, so 45 degrees is a central angle. It's an angle whose vertex is in the center of the circle. So it's 45 degrees. And the cool thing is, the nice thing is, that if I want to talk about my arc of my circle, so the 45 degrees is referring to this angle here, right? The arc of the circle is referring to this. And we would say the measure of arc RS, okay, is also 45 degrees. And because RS is less than 180 degrees, this is also known as a minor arc. So we're just kind of reviewing what we did the last end of class, minor arc. Okay. So what we want to do is we want to know, well, then if arc RS is 45 degrees, what is the measure of arc RTS? So TS is the arc that goes all the way around here. What is the measure of arc RTS? And remember, you get to make that little rainbow, right? Well, the measure of angle arc RTS is the same as the measure of angle, this angle here. Okay. All circles add up to 360 degrees, and we have 45 degrees sliced out of that, right? So if we take 360 degrees and subtract 45, we get 315 degrees. I think you guys all were like, this is easy peasy, right? Excuse me. All right, not on your paper, but who can tell me in the chat, what is the measure of arc RT? So I want to know what the measure of this arc right here is. RT. Anybody on the chat? All right. So I don't know if you guys can't chat or you are not sure, but basically we know that since this is the diameter, it goes right through the center, it forms a semicircle, right? Half of a circle is 180 degrees. And we have 45 degrees kind of chopped out of that. So RT is going to be 180 degrees minus 45 degrees, which is going to be 135 degrees. All right. You guys good? Well, nobody's chatting, so I'm going to assume you guys are good. If not, send me a text message if it's not good. Okay. Okay. This is a quick little postulate. I don't even know if it's on your postulate sheet. I don't think it is, but it's pretty self-explanatory. So, so here we go. Postulate 23, the arc addition postulate. Get a little smaller so I can see the chat. The measures of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. So that's a whole lot of words, okay? But it's basically saying that if you have the measure of arc ABC, so ABC, you want to measure ABC, okay? Then that is equal to the measure of arc AB plus the measure of arc BC. So basically when you're doing arc addition, kind of a weird word, right? You can add AB, so AB, right? Plus BC in purple. And you can add them together to get the measure of ABC. I think that's pretty self-explanatory, right? Add them together, that's what you get. Okay, next up, some examples. So you're ready to do your homework. I can't get it to scroll exactly right, so we'll just do this. Okay, here we go. Money. We're going to check out some money here. You join a new bank and divide your money several ways, as shown in the graph at the right. Find the indicated arc measurements. So if you can type in the chat, oh, I didn't mean to do that. If you can type in the chat type what you think these are, because this should be pretty easy. So the first one is to find the measure of arc BD. Okay, BD. Now, the thing to notice with this is that here's B, right? Here's B up at the top. And here's D down at the bottom. And there's two ways that I can go with this arc, right? I can go to the left or I can go to the right. So if I want to find the measure of arc BD, what are they talking about? Sorry. So when we have BD written like this and we don't have a third point written in, then they're actually talking about the minor arc. So the one that's less than 180 degrees. So which way, going to the left or going to the right, is going to give me an angle less than 180 degrees? I'm going to assume you guys are all talking to your computers at home and saying, Mrs. Ross, we want to go to the left. Because that way is going to be less than 180 degrees, right? There you go. Jake said it. Yeah, so we want to go to the left, right? Or correct to get that. So BD is going to be equal to, if we technically wanted to write this out the right way, right? The measure of BD is equal to the measure of BA, arc BA, plus the measure of arc AD. So we're going to add those two arcs together to figure it out. So BA is 55 degrees, right? And DA is 105 degrees. So when we add them together, we get 160 degrees. Okay. Now, if you had looked ahead a little bit and you looked at your next problem, part B, they want to know what is arc BCD. So BCD actually is the one that goes to the BCD is the one that goes to the right. And we know that that's a major arc because it gives us 3 points. So we need to know, oh, okay, what that's going to be greater than 180 degrees. So it's going to be my bigger number. So there's two ways that you could do this. One is, you know what BD is, right? You know BD is 160, and you know the whole circle is 360 degrees. So you could subtract. Or we could add up this arc plus this arc. All right, so arc BCD is equal to arc BC plus arc CD. So 140 degrees plus 60 degrees, which is 200 degrees. Okay, pretty easy. Sweet. We like easy, right? Example 2, I think you guys can probably do these on your own. Actually, try it on your paper while I get a quick drink of water. So find the same circle up here, okay? Find the measure of BCA. So I'm going to underline this. BCA. Just try this on your own. Here's B, here's C, and here's A. So they want this measure that goes almost all the way around, right? That is a lovely arc. I would just try to draw. I got a BCA. So see if we can figure that out while I get a quick drink of water. Okay. So who got 305 degrees? So if you add up 140 plus 60 plus 105, you should get 305 degrees. Or you could take 360 degrees and subtract 55. Awesome. Okay. Let's shift gears a little bit. So now you're going to kind of think a little bit differently. And we are going to tell whether or not the given arcs are congruent to each other, explain why or why not. Okay. So here we have BC, are BC and DE congruent to each other? So are BC and DE congruent to each other? The arcs, not the angles. So we know this angle and this angle are both 75 degrees. They're congruent to each other, right? So then we also know that arc BC is 75 degrees and arc DE is 75 degrees. So we do know that, yes, in fact, these guys are congruent to each other. That makes sense? They're on the same circle and they have the same measurement. Okay. All right, so what about part B? Part B, we get a little bit tricky here. Okay, so we have arc AB. All right, AB is right here, and we have arc CD right here. CD is in blue and AB is in orange. What do you guys think? Are these guys congruent to each other? So what I haven't been super careful about, but I want to point out to you, is up here, we're talking about the measure. So if you notice up here, we're talking about the measure of arc BD or the measure of arc BCD. So notice these have this little M here, which is talking about the measurement. So we're talking about degrees. When you get down here, and I didn't do a great job of putting this on here. When you get down here, notice that these are written differently. These don't have the measure component where we're talking about the angle. They're just written as arc AB and arc CD. So now when we have this, we're actually talking about the actual length of the arc. So if you took out your measuring tape and you had a circle and you actually measured from A to B, is that the same as the distance from C to D? So the answer to that is no, they're not congruent to each other. The measures of the arc are the same, right? But the measures of the measure of the degree of the arc are the same, but the actual measurements of how far it goes is different. Okay, so hopefully that makes sense to you guys. Because they're two different circles, there's no way they could be the same size, right? All right, and then what about C here? We have FG and HG. So FG is formed by a right angle, right? And the radius of the first circle is equal to the radius of the second circle. So these two are the same circle and they have the same radius. So what do you think? Is the actual arc measurement the same or not? I say yes. They're the same, right? Those two are congruent to each other. All right, I think that's pretty easy peasy stuff. Hopefully you guys followed along. We're good there. All right, on to 10.3. Unless anybody has any questions. Okay. Time for some more theorems. All right, so this is 10.3 is properties of chords. So what is a chord and how is it different than like a diameter or radius? Who remembers? I'm going to assume you're all talking to your screen back there. So a chord is a line segment whose endpoints are in a circle, but it does not actually go through the diameter. Okay, so these two, A, B, and C, D are two chords. So you can see that they're a line. Their endpoints end on the circle. Okay, so it's not a line that keeps going forever. It starts at A, which is a point on the circle, ends at B. And then this line CD is also a chord. So we have a couple of theorems that have to do with chords specifically. Okay, so in the same circle or in a congruent circle. So if you have the same circle or two circles next to each other that are congruent, two minor arcs are congruent if and only if their corresponding chords are congruent. Okay, so this is an if and only if, which means that it works, right, both ways. If and only if means that it goes both ways. And what it says is that two minor arcs are congruent to each other. So arc AB, try to draw it here. Arc AB is congruent to arc CD if and only if line AB is congruent to line CD. Okay, so I think this kind of makes sense. If you have two congruent lines and you're cutting a circle, and those two lines are the same, then you're going to cut the circle, the arcs of the circle, to be the same size. Okay, so here's a quick example of how we could use that. So in the diagram, circle A is congruent to circle D. So these two circles are the same. Okay. Line BC is congruent to line EF. So because we know these two chords are congruent to each other, then we know that the arcs are also congruent to each other. And the measure of EF equals 125 degrees. So find the measure of BC. What would the measure of BC be if the measure of EF is 120 degrees? Well, we just read up here, we just have this theorem, right, that says that two minor arcs are congruent if and only if their corresponding chords are congruent, and it has to be in the same circle. So do we meet all of our criteria here? I mean, so we're in the same circle, right? Or congruent circles. So AD is congruent to circle AD is congruent to circle A is congruent to circle D. Right? That's met. The corresponding chords are congruent to each other. So that means that our corresponding arcs are equal to each other. So that means that the measure of angle B or measure of arc BC is 125 degrees. Okay. Very exciting, right? All right, so make sure you put those on your theorem sheet. Two more. Theorem 10.2. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Okay, so this one's a little bit tricky. All right. So if one chord is a perpendicular bisector to another chord, then the first chord is a diameter. So let's kind of color code this. The one chord that they're talking about, this chord is a perpendicular bisector. So they're talking about this chord right here. And that is a perpendicular bisector to another chord, which is this chord right here. Okay, we know it's a perpendicular bisector because one, it's perpendicular, means it's 90 degrees. Okay, and bisect means to cut into two equal parts, which is labeled on there. So since the blue chord, the one chord, is a perpendicular bisector to the green chord, then the first chord, the blue chord, is a diameter. It goes through the center. So if QS is a perpendicular bisector of TR, then QS is the diameter of the circle. So this is a way for mathematicians to actually figure out, or geometry students to figure out where is the diameter, because if you draw two lines and you can draw one chord as the perpendicular bisector of another chord, then you can figure out that's the diameter. Okay. All right, so then let's take this a little further. If a diameter of a circle is the perpendicular bisector of a chord, then the diameter bisects the chord and its arc. Okay, so this is kind of a little bit opposite, and it has a little more information on there. So if a diameter of a circle is perpendicular to a chord, so here's our diameter, and it's perpendicular to a chord. So we don't know if it's a bisector yet, but if it's perpendicular, then the diameter bisects the chord. So this is the second part. The diameter bisects the chord. Okay, so we'll draw that in blue. This is the then part. So we know that these two are equal to each other. Okay, and its arc. So what it also tells us is that this arc and this arc, it bisects that whole arc. So these two are going to be equal to each other. So if I color code it down here, the purple part tells us that EG is perpendicular to DF. Those are our two lines. Then HD, this little line here, is congruent to HF. So it bisects that line. Okay. And then in yellow, we know that arc DG is congruent to arc FG. Okay. While you have your theorem sheets out, one more theorem to write in there, and then we'll do a couple examples. Okay, I know theorems are very exciting, right? But let's put them all in there at once. This one's a fancy one. Theorem 10.6. Okay, in the same circle, or in two congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, this is another one that I actually think makes sense when you think about it. So we have our if and only if, so that means it works both ways. So you have a circle or two circles that are congruent to each other. If this chord, okay, is congruent to this chord, then they have to be equal distance from each other. Okay, so AB, chord AB is congruent to chord CD if and only if EF equals EG. EG. I know. Don't we all love theorems? Okay, so let me actually show you what this looks like. And I think when you see it, it makes sense. Like, oh, okay. Okay, I've got a circle. Okay, I'm going to draw a chord. I'm going to draw a chord here. Doesn't really matter where. Okay, I have the center of my circle. Okay, oops, I'm trying to do this. This is the center of my circle. So what this says is two chords are congruent if and only if they are equal distant from the center. Okay, so my distance from the center to my first chord, let's say, is, I don't know, draw it here. Okay, and that's, we'll do it from a right angle here. Okay, if I wanted to draw a chord that is congruent to green, and I drew my chord like here, I need to turn my line tool on. If I drew my chord like here, first of all, just looking at them, you know that these two aren't congruent to each other. But look at the distance from the center to this chord is way different than the distance from the center to this chord. But if I'm a little more reasonable and I say, oh, I'm going to make it about the same distance from the center to my next chord. Okay, so I'll make it from here. It's about the same, right? And then I go to draw my chord at a right angle. Then it's a lot more reasonable that my two chords are congruent to each other. Let's try and draw a right angle here. Okay. So this basically, very exciting theorem, I know you guys are excited, says that if you have two chords that are congruent to each other, then they have to be equal distance from the center. Okay, so let's do a couple examples of these. It's going to be mixed with all of our different theorems that we do. All right, so let's actually start with example number 3 here. So make sure you have your theorem sheets that we just did. We're just going to practice using them, okay? So example 3 says, in the diagram of circle E, find the length of BD. Tell what theorem you used. Okay, so make sure you have your theorems that we just looked at. Just by looking at this, what theorem do you think I'm going to use? I'm not going to use 10-6 because I'm not talking about if two chords are the same length, right? I'm not really talking about 10-3 because that's talking about arc length. So I'm definitely going to use 10-4 or 10-5. I just have to figure out what it is. So I need to figure out what the length of BD is, right? And I know already what the length of DF is. So if I can figure out, what I'm ultimately trying to do is to figure out how long this is, right? And I know that part of it is 6, and so I need to figure out what the other part is. You guys probably already have a guess for what the answer to this is, right? So if you look, okay, it says that figure out which theorem you're going to use. So am I going to use 10.4 or 10.5? That's probably the trickiest part. I'm actually going to use 10.5 for this one. Okay, so what it says is if a diameter of a circle, we have a diameter because there's the center and it's going through the center. So AC is a diameter. If the diameter of a circle is perpendicular to a chord and BD is a chord and they're perpendicular, then the diameter bisects the chord at its arc. So bisects means that it divides it into 2 equal parts. So that means that DF and BF are congruent to each other since they bisect each other. So BF would also be 6, and BD would be 6 plus 6, which is 12. Okay, hopefully that makes sense. You guys following along all right? Okay, I'm going to do 2 more examples and then I'll save the rest for Monday so we can kind of review again. And they're not the ones that are on here, so let me take a picture of those. Okay, so this is at the bottom of your notes page. It says number 1. It's kind of all jumbled up. All right, so now we have if the measure of arc TV is 121 degrees, we want to know what the measure of arc RS is. Okay, and you might have some guess just based off of looking at the picture, but we need to know what theorem we can use to actually prove this is true. Okay, so if you go back to your theorems and you look at 10.3, 10.3 says, in the same circle, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So are my corresponding chords congruent? Well, RS is a chord and it's length 6, okay? And TV is a chord and it's length 6. So are these 2 congruent to each other? Yep. So that means that my 2 arcs are also congruent to each other. And so that means that RS is congruent and it's also 121 degrees. Okay. And then the last one we'll do is this number 2. Oh, and just to make sure, you know, this is theorem 10.3. Okay. Find the measures of arc CB, BE, and CE. Okay, so what does this look like? What does it look like I'm going to use? I think for this one, I'm probably going to use theorem 10.4 or 10.5, but which one am I going to use again? So I'm actually going to use 10.5. Okay, which says that if a diameter of a circle is perpendicular to a chord, so I have a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So basically we know that CE, this arc here, if I take a cross section, it's been bisected. So we know that BC and BE are equal to each other because they've been bisected. So that means that 4x up here equals 80 minus x down here. These 2 are equal to each other. So 4x equals 80 minus x. So if I want to solve this, quick algebra, right? Add x to both sides, I get 5x equals 80, or x equals, what does x equal? 16. So if I want to find the measure of arc BC, it's going to be 4 times 16, which is 64. And if I want to find the measure of BE, it's going to be 80 minus 16, which is 64. So these are each 64. And what if I want to find the measure of C to E? That arc is going to be 64 plus 64, which is 128 degrees. Okay, so hopefully that made sense. We'll do a little bit more on that on Monday, and then we'll just keep going from there. So I hope you guys have a good day, and I'll see you on Monday.